All right, MCT4C, we're on our second day of polynomial functions with the familiar and the tried and the true, linear and quadratic. Linear we looked at in grade 9. And we know a lot more about lines than we think we do. The word is embedded. We know what the graph will look like. We know that the equation would look like y equals mx plus b, knowing that m would give us our slope and b would give us the y-intercept. Lines, as you know from last day, are functions because I can draw any vertical line and it will only touch a line in one spot. There is one exception. It's the vertical line, which has a unique equation. X equals a number, and it is not a function because any vertical line will hit that vertical line in way more than one place. But generally speaking, our lines are functions. We know from grade 9 too, at least visually, to find the y-intercept, we let x equal 0. I don't know why it's being funny here tonight. There we are. Conversely, to find x-intercepts, we would let y equal 0. We know if we had a table of values for a line, the first differences would all be the same. I don't know what's wrong with this tonight. There we are. All right, let's look at a couple of little examples. Y equals 2/3 x plus 5. We have a slope of 2/3, which means that our first differences on a table of values would be 2/3. Our y-intercept would be 5, so that we would have a point 0.05 on our graph. It would have a slope upwards to the right. For the line y equals minus 3/2 x minus 7, our slope is minus 3/2 downwards to the right. We would graph it as down 3 over 2. And we have a y-intercept of minus 7. I'm not going to let this win. There we are. Let's look then at quadratics, which were grade 10. We know that a quadratic would graph as a parabola. Could be shaped like this. We know that the equation of a quadratic has an x squared in it plus bx plus c, where the c is the y-intercept. There were other forms for a quadratic, and we spent some time doing some algebra with those, but the form that was easiest to graph was called the vertex form. The first form that I gave you is general form. And lastly, from time to time, we would write a quadratic in factored form. Let me change those letters if you would indulge me, because I would like to be consistent on having my a out here. X minus s, x minus t would do just fine. The last one is called factored form. Factored form. All right. For all three of those, if a is a negative number, then our parabola will open downwards. If a is a positive number, it opens upwards. As a gets larger and larger, if it is positive and gets larger, our parabola becomes steeper or skinnier. Come on, skinnier. Skinnier is not a very mathematical word, but we know what we're talking about. It would open like that if you had a 10 at the front, for instance. Parabolas can open upwards like the one that I have in blue, or downwards. So a parabola could have a maximum or a minimum value at the vertex. So your vertex is that turning point right here or right here, and it can give you a minimum if it never goes lower than that, or a maximum if it has a highest value if it's upside down. So the vertex can give us maximum or minimum values. To find x-intercepts, I'm trying to mirror the things that we talked about with the line. To find x-intercepts, we also set y equal to 0, but that usually meant we had to factor first. A parabola is symmetric. You can see I could fold it in half along that fold line, and it would be exactly the same on one side as the other. We say that it has an axis of symmetry that goes right through the vertex. For example, y equals x squared plus 5x plus 6. We know that the y-intercept is 6, just like on the line. We know that there's an invisible 1 right here, so it is not skinnier or wider than a regular parabola. We call that a normal slope, I suppose. We don't know the x-intercepts in the form that it's in. We may need some review on this, but we could write it in a different form by factoring, and then we would know that the x-intercepts are -3 and -2. Another one, for example, y equals -3x squared plus 2x minus 7. We know the y-intercept for this one is -7, and we know that this one opens downward, and it is stretched, or skinnier. by a factor of 3. This one, because it opens downward, will have a maximum value at the vertex. This would be a really good moment to look at 2.1.1, which you can print off of the website and try those. I'm going to just put the answers here. Get your head back in the line, and quadratic came. Now we're going to look at the same two functions in our new polynomial function terminology. So we have a line, a linear function where m is the slope. So in our terminology, m is the leading coefficient. It's the coefficient in front of the largest power of x. This is really getting frustrating. The degree of the function is 1. That's because there's an invisible x to the 1 there. That's the largest power of x, so that is the degree of the function. For all linear equations, with the exception of that silly vertical line, our domain is all x values. Actually, that's kind of fancy. There we go. All x values where x can be a real number. It's going to go to the left and to the right for the x values forever. The range as well for a line will be any old y values will do. It goes up and down in the vertical direction forever. Two little exceptions. Vertical lines, we won't even write that down, except where m equals 0, which is just silly, and then the range is whatever that number is. For example, if you have the equation y equals 0x, so we won't even write it down, 3, that means your range is only the number 3. Y will not be any value other than the 3. If m is greater than 0, so a positive number, we know what that will look like. It will slope up to the right. We say in our our polynomial function discussion, then, if m is greater than 0, then, as x gets very large, and we write that as x approaches infinity. That's a little arrow, by the way. Then y approaches infinity. So as x gets very, very large, our line goes up to the right. And as x goes in the negative direction, very, very small, our line goes this way. It approaches negative infinity downwards as well. If m is negative, we know what our line would look like. It would slope down to the right. So as our line progresses to the right, x goes to infinity, then our function goes down to the right. It will approach negative infinity. As we go towards the left along our function goes up, positive infinity. We call this end behavior. We look to the very ends of the function and see if it gets very large or if something stranger happens. Similarly, for a quadratic function, let's talk about it with our new polynomial function language. A is the leading coefficient. And that's the one we use to check in behavior. The degree of a quadratic is 2. We get that from the largest power of x. A, the leading coefficient, determines the direction of the opening. Come on. So if A is positive, it opened upward, and it also steepness of curve. All right. We'll look at the two cases. If A is positive and if A is negative. If A is positive, we have a parabola that opens upwards. The domain would be this thing goes to the left and to the right forever. Any x value is acceptable. X can be any real number. The range, however, has a limitation. If it opens upwards, then y has to be greater than or equal to k, the y-coordinate of the vertex. K is y-coordinate of vertex. Not only is this thing bloopy, but it waits, it writes after I write. All right. And y can be any real number as long as it's larger than k, the y-coordinate of the vertex. So here's our vertex down here. All my y values are larger than that value, nothing below it. Larger than or equal to that value and nothing below it. For the end behavior as it opens upwards, as we look at this function going further and further to the right, which is what that means, my function gets higher and higher upwards. So we would say that it approaches positive infinity upwards. If you look further and further to the left, our function also gets bigger and bigger in a positive direction. We would write our end behavior like that. All right. If A is negative, we know that our parabola would open downwards. Something like that. Our domain would still be, x could be anything. It goes to the left and the right forever. But the range has a maximum value at the top. So my y has to be less than or equal to k, the y-coordinate of the vertex, and y is a real number. For the end behavior, as we look further and further to the right, my function is going downwards. So I would say the function approaches negative infinity. As we look further and further to the left, our function again approaches downwards. And so we would write our end behavior like that. I have 2.1.1, which you have already done, 2.1.2 and 2.1.3 as well in the classroom if you haven't printed it off. Still be a good idea, but nothing out of the textbook.